So my name is Cyril Branciard. I will tell you something about quantum processes and correlations with no definite causal order. And since I can see that one of the organizers is back, then I would like to thank the organizers for giving me this chance to come here and talk here. So let me start with a gentle introduction to clarify what I mean by, how does it work? By this no definite causal order, and to try to motivate a little bit what I will be telling you. So this is a very standard model for a quantum computer, the quantum circuit model that we people often use to describe how a quantum computer would work. So how does it work? Well, we have a number of quantum systems here to which we will apply some operations, one after the other, A, B, C. There could be some joint operations here. And those operations are applied one after the other as time goes on. This architecture is actually very similar to a classical computer, where you would also apply some gates on a number of qubits of bits. The difference here, of course, is that you can have entanglement here, you can have entangling operations, and so on. But still, the structure is the same. You have a time ordering which defines what we call a causal order, in the sense that some causal influence can only go in this direction along the circuit, right? And this basic structure of a causal order is at the core of this quantum circuit model. But now we can question this assumption. Is it really the case that we always need to assume that there is a definite order for the operations that you will apply in a quantum computer? So does it have to be the case? And of course, since we know about quantum theory, then we know that we can have some quantum superpositions of states, of cats. So we may ask the question, okay, maybe apart from just superposing quantum states, could we also have some kind of superposition of causal orders? In which case we wouldn't have definite causal orders. So is that something that can be done, that can be verified in the lab? Can it lead to some new phenomena, to some new applications? Could it be a new resource beyond the standard quantum circuit model? So that's some of the motivations for what I will tell you. Then there are also some more fundamental motivations, like can it tell you some directions to take towards a theory of quantum gravity, and some more fundamental for motivations? So this is the outline of what I will tell you. I will show you that indeed you can make sense of some kind of superposition of causal orders in the quantum switch that we already heard about. Then I will introduce, present you the process matrix framework, which was introduced maybe 5-6 years ago by Czeslaw and co-workers in Vienna. And so then there are some concepts that I will introduce, like causal separability or causal nonseparability, and causal inequalities. And this is, I will argue, this is a framework that is well suited to study this kind of situation with no definite causal order, and with quantum superpositions as you have in the quantum switch. And this framework was initially introduced in a bipartite scenario, and I will move to a multipartite general multipartite scenarios and try to give you some ideas of what kind of subtleties arise when we go to more parties. All right, so the quantum switch. So remember this picture with the quantum circuit, where you have a number of operations, and now you ask the question, okay, can I try to superpose the order of two operations A and B? So I have some input quantum state. I will have some output quantum state. I want to superpose the two operations. So indeed, I can do that. I can draw some links like this. And if I want to go to A, then B, I will take this route. If I want to go to B, then A, I will take this other route. And now you can introduce some control that will tell you, okay, which route to take. And you can have a classical control. If it takes the value 0, then you will take the blue route, and then you will apply A, then B. And if the value is 1 for the classical bit, the other way around, B, then A. And of course, we are quantum physicists, so we like to quantize things, and we can now try to make this bit quantum bit, and that will give this kind of operations, in which indeed you will have a superposition of the two orders, A then B plus B then A. Okay, and so this idea was introduced by in 2009, and there's been a number of experiments, even as we heard yesterday, with a untangled version of quantum switches. So the message here is that this quantum switch just doesn't fit in the standard framework of quantum circuits. So it's really something new, and it indeed, that we will see, that defines a new resource, and you can do some new stuff with this. And this morning we heard about an experiment where they demonstrated an advantage for some tasks. So new tasks are made possible. So for the experiment that was presented this morning, mentioned the discriminating problem where you had to decide whether two operations commute or anti-commute. And you can do it more efficiently with this, with a single use of each of the boxes A and B. And there's been a number of other results showing that indeed you get some advantage with this quantum switch. So a new resource, so we need to depart from the idea that there are quantum states that evolve in time, and operations are applied one after the other. So we would like to have a new framework and kind of change the viewpoint, not just follow the quantum states and the operations evolving in time, but have a more global look at the whole process. And this is precisely what the process matrix framework allows us to do. So I should say it was introduced in this paper, not just to describe the quantum switch in a different scenario with more foundational motivations, but it turns out to be really well suited for the study of the quantum switch. So how is it defined? Well, you look at this bipartite scenario where you have two parties, A and B, and then they can perform some operations by X and Y. So this can be choices of operations, and they can get some outcomes A and B. And what Czaslaw and coworkers assumed is that inside those boxes, so we're looking at the correlations described by this probability distribution, and the assumption is that inside the boxes, where everything is quantum. So we should be able to use quantum mechanics to describe what happens in the lab, and this is indeed what A and B will see in the lab. That should be compatible with quantum mechanics. So local quantum mechanics, locally everything is quantum. So that means we can attach some Hilbert spaces for the input, Hilbert spaces for the output, and A and B will apply some CP maps. Okay, and just those assumptions, then Czaslaw and others showed that the correlations must be bilinear functions of those CP maps, and that you must have such a formula that gives you the correlations. So just a trace formula, very similar to the Born rule, where you have the operations applied by A and B in the Cioè-Giamolkowski isomorphism here, and where you can define some matrix that will allow you to calculate the correlations, and they call this the process matrix. So just to give you some more intuition of what this process matrix could be, well, if it's just a quantum state that is sent to A and B, well, the process matrix is just the quantum state, and this is just the very standard Born rule. Okay. You can also consider a situation where you have a quantum channel going from A to B, and in that case, you also get a similar Born rule, where this is the Cioè-Giamolkowski of the channel. So in general, the process matrix will encode everything that is outside of the two labs, and in particular it encodes the causal relations, how the labs are connected to one another. So to be more specific, there could be situations where there is a causal order between A and B, where A is before B, so then there is a channel, there might be some shared entanglement here. In any such case, that's a channel from A to B, and you can show that the process matrix has a specific form. Ognan, Fabio, and Czaslaw then introduced the concept of causal separability, where the process matrix is either of this form or of the form where B is before A, or just a convex mixture of those two. And this is in some sense the standard classical causal order between the two, which may come with a probability Q or 1 minus. All right, so that's the notion of causal separability that they introduced. And of course, it's interesting because there are also processes that are causally non-separable. Okay, so not all process matrices that are built, that are constructed in this formalism, will have this form. Indeed, you can construct process matrices which are causally non-separable, which do not have this form. So that means essentially that they are just incompatible with a definite causal order. There is no definite causal structure that will explain the correlations that you observe. And also what was interesting is that they showed that they can also generate correlations that are themselves incompatible with any definite causal order. Okay, and so if you just look at the correlations, they may violate some causal inequalities, so, which are just bounds on the correlations that can be obtained when there is a definite causal structure. So just to give you an example of a causal inequality, where this is a simple causal game that we already heard about, which is the bipartite game, where A and B are given binary inputs and must output binary values, and the goal is to just guess the other party's input. Okay, and you can easily convince yourself that if there is a definite causal order between A and B, then say for instance A is before B, then for sure B can guess Alice's bit, because she could just send it, but there is no way for Alice to guess the input bit of Bob if it's uniform. Okay, so that means she will only get a half probability to guess the input, and it follows that there is a bound on the success probability for this game, which is just a half, and this is precisely a causal inequality. Okay, this has to be satisfied by all causal correlations. All right. So entanglement, this is this phenomenon that we all know about, that when you have a shared entangled state, then you may not be able to describe it as two separate states. And the way you detect entanglement typically is to measure an entanglement witness. And for that, you will make a number of measurements for Alice and Bob. You recombine the statistics, and you get some value for an entanglement witness. For Bell nonlocality, there is no such theory-dependent description. You're just looking at correlations, and these are just black boxes. You don't need to describe what's happening there. You just look at the correlations, and you see if they violate a Bell inequality. So the point I want to make here is that this is a theory and device-dependent concepts. This is theory-independent concepts, right? And the new concept that I introduced of causal separability or causal non-separability and the non-causal correlations are really the analog. And to understand the difference, it's really the same. These are device and theory-dependent concept. So the analog here to entanglement. And these are theory and device-independent concepts, the analog of Bell inequalities, essentially. And this analogy is quite useful to keep in mind, because then it allows us to better understand the concepts that we are dealing with and to clarify what we are talking about, and also that will guide us to try to better understand these concepts. So for instance, entanglement can be detected by witnesses, and the argument is that a set of separable states is convex, so you can always find a hyperplane that separates any entangled state from it. And the argument is really the same for causally non-separable processes. So for any causally non-separable process, you can always find a separation that defines a causal witness, and that will allow you to verify in practice that you have a causally non-separable process. And this is theory and device dependent. Same for Bell inequalities. Non-local correlations, they can be characterized geometrically. We can construct the local polytope whose facets are the Bell inequalities, where you can do the same here. You can also show that the causal correlations form a causal polytope, which is just obtained as the convex hull of the polytope for those probabilities and those probabilities. And the facets also define causal inequalities. So you can also try to fully characterize the causal correlations in terms of causal inequalities in a given scenario. Okay, so as I said, that framework was introduced independently from the quantum switch, which I presented before. But now I will show you how you can use the framework to describe the quantum switch. So remember the operation that was made by the quantum switch. The first observation is that if you just get rid of the control qubit at the end, then you just end up with just a statistical mixture of the two orders, which is not so interesting. So you really need to keep the control to make the scenario interesting. So we will give it to a third party here. So this will be a three-partite process. And you can actually consider it as a four-partite process if you consider the party here, as it was done in one of the experimental tests. But I will stick to the three-partite description for simplicity. The way you describe it as a process is the following. So let's look at this term here, where A is before B. Then we have this input state that is sent to A. So we will attach it to the incoming state of A. And then there is an identity channel that takes the output here, sends it to B. And this is described with the Choi-Markovsky isomorphism as this entangled state here. So that goes from the output space of A to the input space of B. And then again, an identity channel that goes to C here. And remember, we will keep the control bit, and we will give it to C also. So C prime, the input state of C. Same for the other order. And now, since we have a superposition here, if you want to obtain the process matrix that describes the whole process, you just need to sum those two terms, right? And you get the process matrix. So very easy, very nice. The question is this process matrix that you construct causally separable or not? Well, it's fairly easy to show that it's not. So you cannot decompose this process matrix as a convex combination of those two terms, where one is compatible with A before B, the other one with B before A. Okay. So indeed, you can construct a causal witness, and that was tested in some experiments. Some remark I should make also is that this quantum switch cannot violate any causal inequality. So here we have the analog of a quantum entangled state that wouldn't violate a Bell inequality. Here we have a causally non-separable process, which nevertheless doesn't violate any causal inequality, that is not able to generate non-causal correlations. All right. So that's an argument to show that the switch is causally non-separable. But actually, I cheated a little bit. Because in the previous slides, I only defined the notion of causal separability for two parties. And here I have a tripartite process. Okay? This was fine here because C was at the end. So we can easily argue that the only orders that matter are A before B or B before A, and always C at the end. But still, we want to have a full characterization of a causal separability and causal non-separability in the multipartite scenario. And this is what I will present now, and I will try to insist on some of the subtleties that we have to take care of in those scenarios. So again, the scenario is this one. Many parties with inputs and outputs. We're looking at both the probability distribution that they obtain, and when we open the boxes, we look at the theory or device-dependent description of the whole thing, and we ask the question whether these correlations are consistent or not with a definite causal structure. So that was the bipartite case. So we defined causal correlations as just those that can be written as a convex combination of correlations with A before B and B before A. So let's try to go to more parties. The naive generalization would just be to take a convex combination of every possible order between the n parties. But if you think about that, it's not quite enough to really describe what you would mean by a causal order. Indeed, you could have a dynamical order, where in this case with three parties, you have a first party A, which depending on what happens here, defines the following order for the other two. So in that case, you would then just have a combination of different orders. I want to also describe this possibility of dynamical order, and the causal order that is established as the experiment goes on. So the way this is defined, that was defined by Ognian and Christina in this paper. The argument is that even with this dynamical order, you will always have one party that acts first. Okay, and this could be any party with some probability. So what we will call causal correlations are those that can be decomposed in this way for with some probability party K acting first. So where you can describe what happens at K here. And then whatever party K does, the conditional probability distribution for all the rest should remain causal. Okay, so we have now a recursive definition for those causal correlations. Very nice. Once we have this definition, then we can use the same tricks as before, and also as in the case of locality. We can show that those causal correlations in the multipartite case also form a convex polytope, which you can characterize, and actually the dimensions explode much quicker than for Bell non-locality. So we could only consider the very simplest tripartite case. But anyway, in principle, you can characterize causal correlations this way, and well, the vertices of this polytope correspond to deterministic strategies, and the facets define the causal inequalities. All right, so that was for the causal correlations, the device-independent objects, concepts. Now I want to move to the causal non-separability of processes. So now the device-dependent and theory-dependent description of what's happening. So that's again the bipartite case. And here, if we look at the literature, there are different definitions of causal separability or causal non-separability for n parties that have been introduced. So the first one was this one, which I already used before, and which was considering a case where there's a party which doesn't have any output. So you can always consider that it's last because it will not send anything to anyone. And in that case, it's reasonable to just consider this definition. And pretty much at the same time, Ognan and Christina also considered the full general N-partite case, and they gave a different definition from this one. And this definition was very much inspired by the definition of causal correlations. So that's the definition that I introduced for causal correlations. For causally separable processes, the definition introduced was that a causally separable process should be decomposable in this way, as a convex combination of processes compatible with party K acting first, so very much like this one, and such that whatever party K does, the remaining conditional process now is causally separable. So again, a recursive definition. Actually, there's a subtlety here that was already considered by Ognan and Christina, is that you can also impose in this definition that W is, should remain also causally separable, even if you attach some entangled state here. And so they also introduced this definition of extensible causal separability, which is causal separability also when you attach some entangled state here. So that's one of the subtleties that you get in the multipartite scenario. In the bipartite scenario, that doesn't make any difference. Indeed, they showed that the two definitions are different, and this is what they call the activation of non-causality. So you can have a process which is of this form, which is causally separable, but when you attach some entangled state here, it becomes causally non-separable, essentially. So the situation now is the following. We have two actually quite different definitions. This one, which we used before, and those two definitions of causal separability or extensible causal separability. So maybe too many definitions for just one concept that we want to characterize. And so we looked at whether those definitions were equivalent. And in fact, what we showed is that the definition of causal separability used here is equivalent to what they called extensible causal separability, but not equivalent to this one. Okay. So we are in a situation where we should try to fix a little bit the terminology here. And we argue that this concept of extensible causal separability is the most natural definition that we should work with, essentially because in this framework, those ancillary quantum states should come for free, essentially. And also, it's nice that this definition reduces to a situation that we feel we understand in some particular case. So yeah, the message here is that this should be the right definition to use and to consider. I hope I can convince people, and if you have other arguments to choose another definition, let me know. I should also say that there was yet another definition that was used in this experimental paper, where they just considered a convex combination of two fixed orders, and this doesn't allow for dynamical orders. So this is yet another definition, which is also different from all those definitions. But I think we should stick to just one definition, define the concepts once for good, and I will argue that this is the definition to be used. All right, so once you define your concepts, now you want to characterize causally separable or causally non-separable processes. And so in this paper, they already had a characterization in the tripartite scenario. And this is a kind of pyramidal characterization where a causally separable process can be decomposed as a sum of different terms, where this is a valid process compatible with A acting first, with B first, C first. And this one can be decomposed as two processes, which are not necessarily valid processes, but such that whatever A applies, then the conditional process should be valid and compatible with the order B before C. Okay? And because those are not necessarily valid, it's not just a convex combination of 6 different orders. And this is where this allows, for, in particular, for dynamical causal order. All right, so let's go to more parties now, where we do have a characterization, which is, however, only efficient condition. And this is, again, a pyramidal characterization. So process matrix is compatible with A first. This is not necessarily a valid process matrix, but such that whatever A does, the conditional process is compatible with B, acting after A, and so on. And the interesting thing is that this is equivalent to what we can characterize as quantum circuits with classical control of orders. And this is an open question whether this decomposition is necessary as well. We also have a different necessary condition, which I'm not showing you here because it doesn't look so good. But still, since it's a necessary condition, it allows for the construction of causal witnesses. So now we can also characterize causally non-separable processes in the multipartite case with such witnesses. All right, so let me finish very briefly. I mentioned the fact that we can have causally non-separable processes in quantum theory. The quantum switch is one of the famous examples, and so far they are essentially the only example that we have. In the multipartite scenario, we have some subtleties, so we need to take care of dynamical causal orders. The fact that we can attach entangled systems does make a difference here. I'm also mentioning that we also can define genuinely multipartite concepts, so just like genuinely multipartite non-locality or entanglement, we can also consider such genuinely multipartite non-causality. And yeah, essentially that's a new resource for quantum information processing. Some interesting things to discover here. Probably many applications still to be discovered. So thank you very much.